All right. Great, thank you so much. So I want to talk to you a little bit about sort of some lessons learned about Uber's scaling, and I've been talking about this for a while. So I mean, there's a bunch of stuff out there about, like, I don't know, like Uber got pretty big. You probably like most people know what it is now. Like, it's kind of a thing. I think perhaps surprising to many people is sort of how quickly things are changing. And so I've got a couple of quick little videos to show you the pace of growth in a couple of Chinese cities over the course of 1 year. Is that playing? Oh, there we go. So this is Beijing over from the beginning of a year to an end of a year, and you can just sort of see, like, in one city things are happening like that. This is Chengdu, and it's sort of the same story, and you kind of see, big reveal, you kind of see the same pattern happening in a bunch of cities, sort of all over the world. So this thing is happening really, really quickly. And a bunch of the ways that we have responded to kind of like how to handle all of this scaling, maybe we did the best that we could. They weren't always right, but we certainly learned a lot along the way. Some quick public numbers, because everyone always wants to know. Most of the stats I'm not allowed to talk about, but those are some fun ones. Another fun one is how many engineers we have, which is somewhere around 2,000. And when I started at Uber a year and a half ago, there were 200. And so this is a 10x growth in a year and a half. Pretty crazy. And I've learned in this very short time, I mean, a year and a half doesn't seem like long at all, but in this kind of crazy accelerated path, it seems like forever ago. And I try to think about, like, what could I tell myself a year and a half ago? Like, what advice do I wish that I could have gotten? And a funny thing about advice is you're not always open to hear it. Like, you hear advice when you're ready to hear it. And I think most of my advice I probably would have said, "You don't understand me, man. It'll be different this time. Like, I got this." But I think that there are a few things. There are a few things that maybe I could have gotten through to my young and naive self a year and a half ago. But I think a lot of this stuff, like, man, you probably have to learn it the hard way, like, at least a little bit. So take this advice for what it is. You might have to learn some of these things the hard way, but then maybe you can think back to that one Uber guy was telling me about this a long time ago, and that'll be fun. So here's a graph of our service growth. You'll note it doesn't end at 1,000, even though I said 1,000. This is because we don't have a reliable way of sort of tracking this over time. It's like bizarre, but it's somehow really hard to get the exact number of services that are running in production at any one time because it's changing so rapidly. So there are all these different teams who are building all these different things, and they're cranking out new services every week. Some of the services are going away, but honestly, tracking the total count is like this sort of weird anomaly. Like, we have metrics on everything else, but on actual count of services, sort of not a thing people care about. So yes, I have to use the word microservices. Like everyone else, have microservices, and it's a technology conference, so we had to say microservices a whole lot. And so here we go, I have said it, but I want to try to add a little bit something to this discussion of, yes, it's super great to kind of break up all of your monoliths into smaller things. Monolith, just the name sounds bad. I mean, it has lith at the end of it, right? It sounds like a terrible thing that you would never want, like monolith. But there are probably some sort of similar, like at certain scale, there are some similar kind of downsides, surprising trade-offs about microservices that I want to explore with you here a little bit. And one of them is, if you're building a whole lot of services and you start to accumulate a lot of them, and you might start to wonder at some point whether you could get some of these other cool buzzwords from the industry that, like, database people and programming language people are always like so excited about. They've got their immutability. It changes everything. It's so great. Why can't, at some point, like our microservices, can they be immutable? Specifically, or I mean, additionally, like append-only databases, these are great. Like everyone loves them, you can reason about them, et cetera. But I think similar properties are true of a microservices deployment at some level, in some ways. The time when things are most likely to break is when you change them. So Uber is most reliable on the weekends when our engineers aren't making changes, even though that's when we're the busiest. And so every time you go to change something, you risk breaking it. I think that there is a point at some point, a set of software that's deployed in a microservice, it might actually make sense to just never touch it. Maybe. I don't know. I think we're doing that whether we like it or not, like whether it was even planned out. It was sort of like a surprising benefit that we ended up there. This just sort of all, kind of happened. And, it's worth sort of questioning, like why are we throwing, a lot of engineering effort into this architectural style? Like why are we going to do this? Like, it's not purely by accident. I mean, like, we're definitely getting a lot of good things out of it. Like, obviously, like, we can, it allows these teams, so we're adding people all the time. They need to be quickly formed into teams and, like, get to work on something where they can sort of reason about the boundaries. And so this allows these teams to be formed quickly and move and release independently. Like, that's really good. And we've adopted the own your own uptime, so you run the code that you write. Everyone is on call for, all the service teams are on call for the services that they run in production. And so that's pretty cool. And then it starts to get maybe a little less obvious, but it doesn't mean people say it less often, which is we should use the best tool for the job. But best has so many different ways of being understood. Like, best in what way? Like, best to write, best to run, best because I know it, best because there are libraries, best there are all these like weird, like it sounds so obvious, you can just say it's the best. But when you really dig into it, maybe, I don't know, it starts to get a little shaky. And if you start really thinking about like, well, what are the costs? What are the costs of doing like a big microservices deployment? Right off the bat, now you have a distributed system. And these are way, way harder to work with than a single piece of software, than a single monolithic system. Like, everything is an RPC. All of a sudden, you have to handle all of these different crazy failure modes, all of these different weird behaviors that in a single monolith did not exist. And more importantly, like, what if it breaks? So how do you troubleshoot? How do you figure out if your service is in some chain between something else that's broken? Like, how do you make sure that the right people get paged, the right corrective actions are taken to fix it? But these are still like sort of the obvious things. Like, you can read a lot of people talking about these, and they're sort of obvious if you think about them. But there are some less obvious costs, and I think these are really interesting. First of all, everything's a trade-off. Let me just reiterate that. Even if you don't realize you're making it, everything is a trade-off. Like, you're going to get something in exchange for having all these microservices. Like, you get these things, but you're probably giving some things up. And this happens in more ways than you might think. Like, you might choose to build a new service instead of fixing something that's broken. And I don't know, that doesn't maybe seem like a cost at first. Like, it maybe seems like a feature. Like, I don't have to wade into that like old code and risk breaking it. But at some point, like, the costs of having always building around problems and never cleaning up the old problems, this starts to be a factor. And another way to say that is you might trade complexity for politics. So instead of having to have a maybe awkward conversation with some other human beings, turns out it's all human beings who are writing the software, at least these days still. There are people on the other end of these source code files, and you might have to talk with them, and you might have to have these awkward, human emotion relationships with them. And this is really easy to avoid if you can just write more software. And that's a weird property of this system. You can just write more software and avoid having these sort of awkward conversations. And you get to keep your biases. Like, if, along those same lines, if there are some things that maybe you don't necessarily agree with, or let's just say you like Python, but the team that you're interfacing with, they're writing their stuff in Node.js. You might think that you might have opinions about which one of those languages is better. And instead of maybe helping work in that other code base that is a language that you don't personally care for, you might just build some new stuff in your own language just to sort of, prop up your sort of the things that you think are best, even though that might not be the best thing for the organization or the system as a whole. So these are kind of weird. Like, these are sort of like, I hadn't really considered that by super modularizing everything that we might be introducing these sorts of things. So I'm going to take you through, give you some concrete examples of sort of how we've broken up some of our engineering teams and some of the technology choices that we've made, and you can maybe see how you can imagine, project, if you will, how this might be going down with all the people that work at Uber. So before, in the prehistory of Uber, there was 100% outsourced. There, it didn't seem like a technology problem, so just had some company somewhere write the first version of the Uber mobile app on the back end. But eventually, when the engineering was brought in-house, we had Dispatch, which is all written in Node.js. Well, these days, that team is writing all their new stuff in Go. The core services, which is kind of like the rest of the system, was originally written in Python, and now that team is moving to Go. And eventually we brought maps in-house, and so that those teams are using Python and Java, and we have a whole data engineering whole group that their stuff's written in Python and Java. We've got an in-house metrics thing that we've written, that's written in Go. And you start to notice, wow, that's like a lot of languages. And we could do that. It was great. Microservices let us do that. We could just have teams be writing in different languages, and they're still communicating with each other, and that's cool, except we hadn't really counted on or factored in what all the costs would be of operating that way. So the first obvious one, okay, fine, yes, hard to share code. Simple, no surprises there. But it's also kind of hard to move between teams. If you want to sort of reorganize some people, and now you've got a whole bunch of knowledge built up inside of people's heads in sort of one platform that maybe doesn't directly translate to some other platform. And they can learn, anybody can learn, but there's a cost, right? There's a switching cost of moving between teams. And so what I wish I knew before kind of thoroughly embracing this microservices everywhere model is that by having multiple languages, it can fragment the culture. You can end up with sort of camps of oh, I'm a Node programmer, or I'm a Go programmer, and Java, don't care for it. People have, it's natural, human beings organize around, tribes or whatever, but by embracing this, we can have lots of languages everywhere. There's nothing to sort of check that tendency. And there's a real cost there, and I'm not sure exactly how to appropriately address those costs, but surprise, there is a cost. So, like I said, everything becomes an RPC, and that has a lot of surprising issues. When teams are communicating with each other with RPCs, that's the way that they're talking to each other. So right off the bat, when I started, we were doing everything with HTTP, and wow, this is a very common path that a lot of people go down, but at scale, especially with lots and lots of people joining really, really quickly, the weaknesses of something like HTTP really start to show up, what's a status code for? What are headers for? What goes in the query string? Is this RESTful? Oh, what method is it? What does that mean? And all of a sudden, all these subtle things that seem really cool when you're doing browser programming, all of a sudden become very, very complicated. And what you really just want is to say, I run this function in this, over there, as opposed to here. Tell me what happened. But instead, now you have all these weird subtle interpretation issues with HTTP semantics. And yeah, that's surprisingly expensive. And JSON, again, super fun. It's neat that you can just look at it with your eyeballs and read it and just see UTF characters there. But without types, it is a crazy, crazy mess but not right away. It's just you're sort of borrowing against a future crazy mess when someone will change something and then maybe a couple hops downstream, they were depending on some subtle interpretation of like empty string versus null versus some type coercion deal or whatever in one language versus the other, and it will cause like a huge mess that takes forever to sort out. And what we could have fixed all of this if we had just had types on all these interfaces. And all of these things like that seem so great at like small scale or when doing browser programming end up being like real costs at scale, especially at big team scale. Of course, RPCs are slower than just like making a function call inside a browser, but especially as you move absolutely everything to microservices, the cost of making these things starts adding up. So what I wish I knew is that servers are not browsers. Like, talking across the data center, it makes way more sense to treat everything like a function call than it does to treat it like some kind of web request that you might want to cache and fetch over the internet and have all the extra browsery stuff. When you control both sides of the interaction, it's way better for everybody to treat it like a function call. So how many repos is best? This is a thing that I never thought, a discussion I never thought I would have, because I thought the answer was obvious. One is what I thought, but it turns out many people disagree with me. And many people think that many repos is the right answer. Maybe one repo per project, maybe multiple, like who knows? Because, you know, it's kind of like the trend in the industry of like publishing many small modules, and it's very open source friendly, right? Like you have, if you break everything into nice small modules, then it's really easy to just open source some part of it or swap pieces of it out. But on the other hand, one repo is really great because then you can make cross-cutting changes. If you want to change something in two services at the same time, it's really easy. You can browse the code really easily. So, you know, there are definitely trade-offs. And, you know, many is bad because, like, it's really going to stress out sort of your build system, your navigation ability. It's really, it's kind of painful to make sure that you've done a cross-cutting change correctly, or even that you have all the right code. And one, of course, is bad because eventually, like, it's going to get so big that you won't be able to actually build your software or even check out your software unless you have some elaborate, crazy system that you know goes through heroics to allow you to preserve this illusion. Like the system at Google. Google famously has one repo, but kind of because it's so large you could never actually check it all out. So instead, they have a virtual file system layer that like lets you pretend that you have it all checked out, but you only actually have the stuff checked out that you're actually working with. Wow, one repo, super cool, but probably not usable without specialized tooling. So here's a glimpse of how many repos we have at Uber. I took this a month ago, and this is also apparently not tracked anywhere, so I just happened to have looked at it a month ago. And so in our internal Git repository, there are over 7,000 repos a month ago, and now there are over 8,000 repos. So that's a lot of repos. And if you sort of filter out, like, okay, like individual engineers might just want to put up a few of their own little projects as individual repos, and some teams track the configuration of their service separately from the service itself, and so these are like the configuration repos. But you can see, like, that's still not the majority of them. I mean, there are just a lot of repos out there. We are so far to the other side of the many continuum on the one versus many that I fear that there's no way to ever become a single repo. I don't know. Maybe. We'll see. So in this big, this big like microservices deployment, like there are a ton of operational issues that come up. Like I mentioned, well, what happens when things break? So yeah, there are downstream dependencies. Like this is really complicated. But back to the people issues, there are some surprising things that some surprising situations that will come up is when other teams maybe are blocked by you because you're not ready to release your thing, but they have to put a fix into your service. But here you are owning your uptime, but now some other teams dependent on you, and so can they release your service? Like if all your tests pass, or like I don't know, is all of your automation good enough that other teams can release each other's software? Like I don't know. That's an interesting problem, and for us, it sort of like depends on the situation. Like sometimes yes, but sometimes, like usually no. Like usually you just have to be blocked by the other team releasing their thing, and you just got to coordinate, and it's kind of, time expensive. But I think that the real big realization, for me was that we really want to understand, like we went to one side of the trade-off with microservices. We said, yeah, great, small teams, everybody's moving fast, they're all releasing features super quickly, they're iterating, they're owning their own uptime, et cetera, that's all great. But sometimes you have to understand the whole service as one thing, as one top level working together as one giant machine system, and that is kind of hard when you spent all this time breaking it up. So we just got done, decomposing it as much as possible, and now we have to somehow re-understand that all as one. This is a tricky problem, and I wish that I had spent more time kind of keeping that context together of we should really understand, we should still be able to understand the whole system working as one. So performance, it's definitely going to come up when teams are talking through each other, to each other over RPCs. RPCs are expensive, and especially when there are multiple languages, the answer for how you understand your performance, it totally depends on the language tools, and the tools are all different. And so now we've just gone through this process of allowing people to write in all these different languages, but now understanding the performance across those languages becomes a real challenge. So maybe in Go, you might have something like this pprof output, which is pretty sweet, but not all runtimes have this. So what we have been doing is to try to get everything, to get the performance tools, that all the languages that we run to have a common sort of profiling format, which is flame graphs. So this, for example, is a flame graph from a Go program, and this is a flame graph from a Node program. And we have similar deals with Python, and I'm pretty sure we have this just about worked out with Java at this point, although there's some weird other deals where some things in Java are hard to capture performance-wise. But anyway, the goal, the point of this, though, is that as you move around and want to understand the performance of the system, if the tools are so very different from one side to the other, that is another big point of friction when you're trying to chase down a performance problem and the tools are different. The other big thing that I learned that was surprising was everybody wants to get a dashboard, some performance dashboards like this, but if it's not generated automatically, teams will just end up making their own fun little dashboards of things that they think are important, and then when you want to try to trace some problem down, one team's dashboard will look all totally different than another. And what we should have done earlier, and what we're doing now, is make it so every service, when you create it, you get the standard dashboard with the same set of things that we all agree are useful things to know about from your service, and you get this without having to do any work at all. It just shows up, you have a service, and now you have these dashboards. So then you can always browse everybody else's stuff, and it will all sort of look the same. Another big debate performance-wise is whether you should even care about performance. Performance, premature optimization, root of all evil, et cetera. It's spawned, that phrase has spawned a very weird subculture in our industry of people who are literally against optimization because they're just it doesn't matter, this is not that busy, the service doesn't have that much traffic, we should always optimize for developer velocity. We can always, buying computers is cheaper than hiring engineers. And there's a certain truth to that. I mean, engineers are indeed very expensive and getting more expensive all the time, whereas computers are getting cheaper all the time. So that definitely is, there's some truth to that. But the problem is that performance doesn't matter until it does. One day, you will probably have a performance problem, and if you've kind of established this culture of, no, performance does not matter, we'll just get more computers, it can be very, very difficult to actually have it suddenly matter if you're, without the kind of infrastructure necessary to sort of deal with these sorts of things. And so what I think is, you probably want to have at least some kind of minimum requirement, some kind of SLA that's performance-based on everything automatically that gets created, whether or not it's even a usefully fast number, just so that there is a number. maybe set it to 20 seconds, but just make it so everybody has a performance SLA that they just have to have. Whether they don't have to opt into it, they can opt into a more aggressive amount, but everything has an SLA, and then that way you can always lower it. You can always bring it in, and there will always be just that safety net of at least we have a way to, a knob that we can turn. So, what I wish I knew is that, good is not required, but you have to at least know where you stand. And it's maybe not now, but it will be eventually. So related to performance is this notion of fan-out, which causes a lot of performance problems. And this has some kind of, sort of obvious at first side effects, but a little subtle if you've never dealt with this problem before, which is the overall latency before you can respond to the user, right? You've got to wait for whatever the slowest thing you have in your call chain. And so imagine a typical service that, it's generally pretty fast. It responds in 1 millisecond 99% of the time. That's pretty good. But 1% of the time, unfortunately, it takes a whole second. Still doesn't sound too bad, right? Well, it's a bummer, but 1% of the time, my users are going to get the slow case and oh well. And that's pretty basic, but if you suddenly start having big fan out, the chances go up pretty quickly, and suddenly more and more and more of your users are hitting somebody's slow case somewhere. And this gets even worse if you're not on the P99. If you're on the P95, it only starts taking a few fanned out service calls before suddenly you start hitting the slow case way more often. So the best way to sort of go after these kind of fan-out problems is to get some kind of distributed tracing. There are lots of ways to get this. You can get the Zipkin, or now this open tracing project is pretty cool. We're participating in that. That is a great effort. But if you don't have that kind of a scale, you can just use logs. Just plumb a common ID through every request and just put it in your log message. Without this kind of tracing, without a way to understand a request's journey through the architecture, understanding these sorts of fan-out problems is really, really difficult. And I will give you some examples. These are actually from our production Zipkin deployment of sort of why some of this stuff is so hard to track down. So this one, I'll start with an easy one. So this one, super obvious, classic. A request is working its way through the system, and then all of a sudden, somebody took a long time, and the results of the services down below, they kind of all depend on that. And it's really straightforward, no tricks. Let's just get in there and figure out why every now and then that thing is too slow. But here's a trickier one, which is there's a huge fan out, and it turns out it's to all the same service. And what you see is that, yeah, of course, the top level service, it took it it was a long time before it could respond. But each of the individual service calls into this thing below it are kind of the same speed. And they're not that fast. I mean, this is not a blazingly fast service, but I can't even remember what it does on each request, but it does something that takes some time. But still, they all take roughly the same time. And so if you ask that team, hey, it really seems like something might be wrong with your thing, and they'll look at their graph and they'll be like, no way, man. Our stuff is super fast. It's really consistent. It's responding really well. But it turns out that there's this massive fan out. Now, this is a case of unintentional fan out where the top level service was fetching a list of things, and then that list contained a bunch of IDs, and then it was going out and resolving those IDs one at a time. And so it was making a whole bunch of concurrent RPCs. You can see how it's got a sliding window of a bunch of pending requests, and as some of them finish, it can fire off more of them. But this is just silly, right? There should just be a bulk resolve endpoint where you just ship the whole thing, the list of IDs that you want, and it just sends them all back to you. But we never would have found this if it had not been for tracing, because these things, they sort of confuse a lot of the common metrics. So here's another one. This one, the fan out is super, super fast. The requests are super, super fast, but the amount of them is many thousands. And what's going on here is there's an ORM involved. And the service gets back an object that looks like a regular old object that you might loop over or change things in a loop on. But it turns out when you do that, every time you change one of these properties, due to magic, it turns into a database request. And so all of a sudden, this seemingly innocent traversal of a collection turns into 10,000 database requests. Whoops. So anyway, but you can if you ask the database team, like, how's your thing going? They'd be like, yeah, we are serving requests so super fast, like, you guys got nothing to worry about. Everything's great. But by the way, why are we doing like 1 million, transactions per second or whatever? Because turns out they're pointlessly doing these tiny, tiny little operations. So you probably want to get some kind of a tracing, to understand the Fanout. Another surprising thing about this is the overhead from tracing can actually change the results. So it turns out it's a lot of work to actually do all this like tracing stuff. And so you probably want to not trace them all, but trace a statistically significant portion of them, like 1% or something like pretty low, is I think what we do. But really, this is not too surprising. But the real surprising thing to me anyway was implementing this kind of tracing behavior requires cross-language context propagation, and this is in the way of so many other problems that we have right now. Which is because we have all those different languages and they're all using different frameworks. If we want to plumb through some kind of context about the request, like what user it is, or are they authenticated, or what geofence are they in, or like, I don't know, like there are all these things that we want to do. And that becomes very, very complicated if there's no way to, if there's no place to put this context where it will be propagated. And specifically, I mean, if you take in a request and you make dependent requests based on that incoming request, will you add in this incoming context without even understanding it? So there may be like fields in there that the intermediate service doesn't even understand, but it will send them along the way to the ones down below. This would have saved us so much time and hassle had we added it a long time ago, or just prioritized adding it. But it just kind of didn't seem that important, and turns out it is. So related to tracing, of course, is logging. A big, perhaps it's no longer a surprise, you're probably starting to see the pattern here, but with a bunch of different languages and a bunch of teams and a bunch of people who are all very new, half the engineering team has been here less than 6 months, so like that's, everybody's pretty new. Everybody might tend to log in very different, incompatible ways, and I think the answer there is to give everyone the structure, like the mandate, mandates are tricky, to give them tools that are so obvious and easy to use that they wouldn't do it any other way, to get consistent and structured logging. And of course, multiple languages make this hard, but even worse, when there are problems, logging itself can make those same problems worse. So something bad starts happening, it's like you start logging a lot. Now you've actually got a whole new problem caused by like logging too much. And then that can cascade, et cetera, et cetera. So having some kind of back pressure in the logs where you'll actually just drop log messages if you can't log fast enough. We're slowly rolling that out to the various different platforms, but wish we had put that in there sooner. But more importantly than all of that is, I wish that we had added some notion of accounting for all log messages, because what happens to all these logs is generally they get like indexed by something like an Elk or a Splunk or a some Hadoop, some kind of a thing takes all these log messages and let's build indexes on them so that people can like search through them and like learn things. But the amount of data that people log, like if it's free, some people will log way more than other people without malicious intent. They were just like, I don't know, logs are free, right? I just made them, and without having some way to sort of trace which somebody to send a bill to. So when the big Elasticsearch cluster that has to index all these things starts running into capacity problems and needs to prune something, like somebody can get that like feedback that, hey, maybe slow down with the logs already. So we open sourced a thing that we're building a lot of our new stuff with on the Go side called Zap, structured logging. My favorite part about it though is how fast it is, 0 allocations on every log, so you might want to check that out. Another thing that that comes up when like a problem surprises that contains surprises is around load testing, and so we want to we want to do these load tests like before things go into production. Of course, that only makes sense. But unfortunately, there's no way to build as big of a test environment as there is a production environment, and even worse, there's no way to actually generate realistic traffic that will exercise kind of all of the problems that are lurking out there. And so what we have started to do is run these load tests against production during off-peak times. And this causes a lot of strange problems. The biggest one is that blows up all the metrics. Suddenly everyone thinks that we're having way more traffic than we actually do, and that's, in order to fix that, we're back to this context propagation problem again of if you're load testing production, but you want people to not think that we're getting denial of service, you have to make sure that all of those requests have some kind of context that says this is a test request, like don't increment the counters and don't freak people out, and that has to plumb all the way through the system. Otherwise, like someone's gonna get sad. But what we really want to do is we want to run load against all of our services all of the time, even when there is excess capacity, because we keep having these bugs where there are latent bugs that only show up when the traffic hits its peak. So we want to keep our systems near their peaks, just shy of them, and then back off as the real traffic starts ramping up. But that just makes this problem even worse. So I wish we had started building systems a long time ago that knew how to handle this test traffic and sort of account for it differently. So if you just saw Casey's talk, like that was very relevant stuff. I was already super on board with this idea of failure testing, Chaos Monkey, etc. It's super great. Not here to try to convince you of that, but a surprising thing that I found when getting this done was that not everybody likes it. In fact, a lot of people hate it, especially if you have to add it in later. So imagine you've written the service and you think it's pretty great, and then you put it in production, and then someone comes to you and says, oh, hey, by the way, we're going to start killing your thing now. Like, you will feel bad, like, that's my baby, I just spent all this time making it, and now you're gonna kill it, and it's probably gonna, users are probably gonna notice, and like, this is gonna be bad. So what I wish that we had done is made failure testing happen to you whether you liked it or not. This is not a decision, this is just part of going into production, is you just have to withstand these sorts of random killings and slowings and perturbings of your operation, because people probably won't want to opt into it. So another big surprise was migrations. A lot of times people come, hear like big companies come and they talk about how amazing their technology is or whatever, and it's always like the new stuff that they just got working, and that's why they came to a tech talk, because they want to talk about their new stuff. And meanwhile, you might think, oh no, my stuff, it's like really bad and old, and we spend all our time doing migrations, and it's mostly legacy. Most of our stuff is legacy. Well, no surprise, all of our stuff is legacy. It's all migrations. Mostly like people who work on the storage, like all they're doing is migration. They're just like some constant migration from one piece of legacy to another not quite so legacy thing. Someone is always migrating something somewhere, and that is, I'm pretty sure, what everyone is doing, in spite of what you might think when people come to conferences and give you awesome talks about their new tech. Because you know what? The old stuff still has to work. Like, you have to keep that business working. There's no such thing these days as a maintenance window. There's no like going down to work on your service. Like, even in off-peak times, as you become a global business, there are no off-peak times. Like, it's always peak times somewhere, right? And And remember what I said before about like, well, what happened to like these immutable microservices? What are you like migrating? Well, that turns out to be the problem with making, just abandoning things at some point, as long as they keep working, is at some point you might need to make some kind of a cross-cutting change, and that's going to be very expensive. If people haven't touched that code in months and are afraid of ever touching it again because the last time we released it, it was 6 months ago, that is a tricky problem. And what I really wish that I knew was that mandates to migrate are bad. I knew people wouldn't like it. Like I knew it's like I never want to be told that I have to like adopt some new system, but specifically being, making someone change just because the organization needs to change versus offering a new system that is so much better that it will just be obvious that you need to get on this new thing. I wish I had placed the appropriate priority on like pure carrots, no sticks. Anytime the sticks come out, I'm convinced it's bad. I mean, unless it's for like security or compliance reasons. I think those are kind of like the two trump cards where it's probably okay to like force people to do stuff. But as a someone working on architecture or infrastructure, I think the carrots are the only way to go. So here's another surprise. Open source is super fun, right? Everybody loves open source. The build by trade-off remains a non-unanimous, non-commonly understood concept. Not everyone agrees where you should, what you should build and what you should buy, what you should use from open source, or what you should build internally. I would observe that anything that seems like infrastructure, anything that seems like it's part of the platform and not part of the product, even if it's something that just makes sense for you to build for yourself, at some point it is on its way to becoming an undifferentiated commodity. Amazon's going to offer it as a service, or someone's going to offer it as a service, and eventually that thing that you're spending all your time, like kind of this platform you're spending all your time working on, someone else will do for cheaper and better. And as long as you have that perspective, I think that's very, very healthy. But what I was surprised to learn is this will make a lot of people sad. A lot of people get really invested in their work, and if they're working on some kind of like lower level infrastructure platformy kind of thing, it doesn't sound good to hear that Amazon has just released your thing as a service. Like you still kind of try to rationalize why we should use your private thing or whatever, and this is not obvious. And it's again back to it turns out there are people on the other end of all these text editors. I wish that I had known that how different the understandings of this trade-off are amongst in our industry. Which brings us to politics. So these services, by breaking everything up into small pieces, it can allow people to play politics. So it's useful. Politics is one of these funny words. Like a lot of people throw it around, but I don't actually think everyone knows what it means. A colleague of mine has a really great definition that I like. He says that politics happens whenever you violate this property. So if you make a decision that violates this property, where you put the values of yourself above those of your team, or the values of your team above those of the company, that anything, decisions that violate this property are politics. A funny thing is that in many environments, like politics just means things I don't like. Oh, that thing happened, I don't like it. Politics, like that's the obvious reason, right? But I think seriously, like this property here is a useful one to consider, and it's one that by embracing highly modular, rapid development, hiring people very quickly and trying to release features as quickly as you can, there is a temptation to start violating these properties, because when you value shipping things in sort of like smaller individual accomplishments, it can be harder to sort of prioritize what is better for the company. Surprising trade-off. But everything is a trade-off, and I think that if there's one thing that I learned from going through this process, it's that I wish that I knew how to better make these trade-offs intentionally. Like, understand, like, when things are just kind of like happening, like, without an explicit decision, just because it seems like this is just the way things are going, it's just the momentum is heading in that direction. Like, I wish that I had thought about what trade-offs were being made, even though I wasn't explicitly, like, we weren't explicitly making them. So anyway, that's all I have. Thanks a lot.
We have time for one question, and there's like 30 questions here, so...
Oh, dear.
Right. Given that you use RPC REST, how do you avoid coupling between your services?
How do I avoid what? How do you avoid coupling? Oh, I don't know. I mean, we don't in many cases. I mean, we do our best, but like it happens. Like, yeah, that's part of the problem. I mean, there's duplication sometimes, and there's coupling sometimes, and we try to like exercise good engineering discipline, and like we try to do failure testing and making sure that like we surface like unexpected couplings, but sometimes there just is, and especially like for like downstream availability, like a lot of times there's just nothing you can do if a service there's some service like three down the chain that if it's down, there's actually nothing, there's no useful answer that you can degrade to, and that coupling just exists. But it's important to remember what the trade-off is. Even though there's coupling, the teams can still move independently. They can still release their components independently and monitor them, understand them, etc. But sometimes it does happen.
Okay, thank you. Remember to vote in the app. Have a good break.